Alrighty then, okay. So we'll get started with, okay, bitwise operators. That is the topic for today. The bitwise operator takes operands of integral type that use a collection of bits. These operators let us test and set individual bits. Okay. Test and set individual bits. Okay. So as we'll see here, we can also use these operators on a library type named bitset that represents a flexibly sized collection of bits. Okay. As usual, if an operand is a small integer, its value is first promoted to a larger integral type. The operands can be either signed or unsigned. If the operand is signed and its value is negative, then the way that the sign bit is handled in a number of bitwise operations is machine dependent. Moreover, doing a left shift that changes the value of the sign bit is undefined. Oh. Because there are no guarantees for how the sign bit is handled, we strongly recommend using unsigned types with bitwise operators. Okay. We have a bitwise shift operator. we have already we've already used the overloaded version of these operators. Where the IO library defines that the IO library defines to do input and output. The built-in meaning of these operators is that they perform a bitwise shift on their operands. They yield a value that is a copy of the possibly promoted left-hand operands with the bits shifted as directed by the right-hand operand. Okay. The right-hand operand must not be negative and must be a value that is strictly less than the number of bits in the result. Otherwise, the operation is undefined. Okay. The bits are shifted left or right. Bits that are shifted off the end are discarded. Okay. So these illustrations have the low order bit on the right. These examples assume char has 8 bits and int has 32 bits. Okay. So 0, 2, 3, 3 is an octal assigned char. Okay. So that is 8 3 is 24 plus 8 16 is whatever it is plus 3. Okay. So if we left shift it by 8 bits promoted to int and then shifted left by 8 bits. Okay, so this whole is here by 31. Okay, leftmost bit discarded. I've seen right shift 3 bits, rightmost bit discarded. Okay. So it goes 1 2 3 and then only this amount is left. The left shift operator inserts value 0 valued bits on the right. Okay. The behavior of the right shift depend on the type of the left hand operand. Okay, if the operand is unsigned, then operator insert 0 valued bits. If the type is signed, the result is implementation defined. Either copies the signed bit or 0 valued bits are inserted on the left. Okay. Bitwise NOT operator. The bitwise NOT operator is this. Generates a new value. Okay, the bitwise NOT operator generates new value with the bits of its operand inverted. Each 1 bit is set to 0 and 0 bit is set to 1. So when we here our char operand is first promoted to int. Promoting a char to int leaves the value unchanged but adds 0 bit to the high order positions. Thus promoting bits to int adds 24 high order bits, all of which are 0 valued. The bits in the promoted value are inverted. Okay, bitwise and bitwise XOR. Okay, the bitwise The AND or an XOR operator generates new values with the bit patterns composed of its two operands. Okay, so unsigned char. Okay, if we take OR, then this will be 1 1 1 1 1. Okay, with exception. If we take AND, then if it is a 0, it will be a 0. So 0 0 1 0 0 1 0 0 1 0 0 1 and 0 1. Then XOR, if both bits are different, then it will be a 1, else it will be a 0. So see, 1 1 0 1 1 0. Ah, right. And then again a 0, then 1 0 1 0, then 1 0. Alright. For each bit, for each bit position in the result, for each bit position in the result of bitwise AND operator, if the bit uh, if the bit is 1, the bit is 1 if both operands contain 1. Otherwise, the result is 0. For the OR inclusive operator, the bit is either 1 or both operands contain 1. Otherwise, the result is 0. For XOR operator, the bit is 1 if either but not both operands contain 1. Otherwise, the result is 0. Okay. It is a common error to confuse the bitwise and logical operators. For example, to confuse the bitwise AND with the logical AND. The bitwise logical, the bitwise this with the logical not. Right. As an example of using the bitwise operators, let's assume a teacher has 30 students in a class. Each week, the class is given a pass-fail quiz. We'll track the result of each quiz using one bit per student to represent the pass or fail grade on a given test. We might represent each quiz in an unsigned integral value. Okay, long 8 bytes. So we will have 64 bits. We define quiz 1 as an unsigned long. The quiz 1 will have at least, yeah, it will guarantee it, at least 32 bits on the end machine. We explicitly initialize quiz 1 to ensure that the bits start with well-defined values. The teacher must be able to set and test individual bits. For example, we'd like to be able to set the bit corresponding to student 27 to indicate that this student passed the quiz. We can indicate the student 27 passed by creating a value that has only explicitly turned on. If we then bitwise OR the value with quiz 1, all the bits except 27. Okay. If we bitwise OR the value with quiz 1, all the bits except bits 27 will remain unchanged. Okay, this is essential. Okay. For the purpose of this example, we will count the bits of quiz 1 by assigning 0 to low order bits, 1 to the next bit, and so on. Okay. So we can obtain a value. You can obtain a value that student 27 passed by using a left shift operator on an unsigned long integral. Okay. So we can obtain, so generates a value with only bit number 27 set. Okay. One UL has a 1 in the low order bit and at least 31 zeros. We specified unsigned long because ints are only guaranteed to have 16 bits, and we need at least 30 27. This expression shifts one bit left 27 position, inserting 0 bits behind it. Okay. Next we OR, right. Next we OR this value with quiz 1. Because we want to update the value of quiz 1, we use compound assignment operator. Okay, indicates student 27 has passed. Okay. Indicate. Okay. So imagine. Okay, the operator executes analogously to plus equals to, it is equivalent to, yeah, okay. So this will have higher precedence than this, I suppose. Then we have imagine that the teacher re-examined the quiz and discovered that student 27 actually had failed the test. Okay. The teacher must now okay, that is how you set up it. Okay. Imagine the teacher re-examined the quiz and discovered that student 27 actually had failed the test. The teacher must now turn off the bit 27. Okay. This time we need an integer that has bit 27 turned off. Okay. And all the other bits are turned on. Okay. So we'll use bitwise AND this value with quiz 1 to turn off just that bit. Okay, we obtain a value not. Okay, so if we not it, then rest are zeros. Then we end it with, okay, we obtain a value. Okay, imagine the teacher can this time. That is how you do that. Okay, so we not the result, then we end it with the, okay, we obtain a value with all the bits 27 turned on by inverting our previous value. And then the value had 0 bits in all but bit 27, which was a 1. Okay. Applying the bitwise not to that value will turn off bit 27 and turn all others. Okay, when we bitwise AND with value with quiz 1, all except bit 27 will remain unchanged. Okay. Finally, we might want to know how the student at position 27 fared. Okay. So here, okay, we want to check if the bit is set or not. So we AND with the result. Okay. Here we AND a value that is a bit 27 turned on with quiz 1. The result is non-zero if the bit 27 is on, otherwise it evaluates to 0. Again, checking if the bit is set or not. Shift operators aka IO operators are left associated. Okay. Although many programmers never use the bitwise operators directly, most programmers do use overloaded version of these operators for IO. Okay. An overloaded operator has the same precedence and associativity as the built-in version of that operator. Okay. Therefore, programmers need to understand the precedence and associativity of the shift operator even if they never use them with their built-in meaning. Okay. Because the shift operators are left associative, the expression, okay, so it will this, then this, executes as. In this statement, the operand high is grouped. Okay, in this statement, the operand high is grouped with the first left shift symbol. Its result is grouped with the second, and then the result is grouped with the third. Okay. So because the shift operators have mid-level precedence, lower than arithmetic, okay, lower than arithmetic operators, but higher than relational, assignment, and conditional operators. These relative precedences, okay, so first we'll add, okay, parentheses, okay, attempt to see out 42, okay, attempt to compare, okay, these relative precedences level means we usually have to use parentheses to force the correct meaning of the grouping. Okay. The last cout is interpreted as this, then comparing cout with 42. We say write 10 onto cout and then compare the result of that operation. Okay. What is value q on a machine with 32-bit ints and 8-bit chars? You flatten one character set in which q has a bit pattern of this. Okay, what is this? This is 8th, right? So 64, 32, 96, 96 plus 16, 112, 113. Q is 113. Okay. What is the value? What is the precedence? Is the not logical operators? I think this has more preference. So these will be zeros, then 1, 1, 1, 1, 1. Then we shift it by 6. Okay. In a grading example section, what would happen if we used unsigned int as a type for quiz? Okay. Is guaranteed an int will be at least 16 bits. So even if we use and if we use uint and it is 16 bits on that machine, then our program logic for maintaining quiz marks for 30 students will be wrong. Okay. What is the result of each of these expressions? Okay. So we AND it, right? So rest are zeros. So this, my guy, is 4 plus 3, and this is 0, 0, 1, 1. Okay, so if we AND it, this will be equal to 1, 1, which is 2. Let me write. This is 1, 0, 1, 1. This is 0, 1, 1. right? Okay, if we AND it, answer will be 0011. If we check, answer will be 1. If we OR it, answer will be 1011, and then it will be 1 either way. Okay, so I just have to check this. So section 4.8, 4.8, and this is 4.25. Okay, and this is left shifted by 6. Okay, so we not the result, or do we shift the result first? Logical operators have low precedence, I think, so we will shift the result first, then we'll not it. Okay, yeah, it is left associative. Dude, are you kidding me? Okay, no, you are not. You're correct. This is 100 and okay, minus. Hold up. Okay, so I have to. Okay, this is minus 726. 7,000 something, right? 7296. 6. Okay. So let me just quickly check. Right. So we have, yeah. Okay, so these operators have more than left shift operators. Right. Okay, so it nots it. So this 0, 0, this is 1. I should see 0, 0. Okay. Okay, so 1. If I copy this, right. Let's go, programmer. I want it negative 7296. Right. Okay. So shifted by 6 bits, right? This is supposed to be a 0. I signed minus 7296. Check it up on decimal to binary. minus 7296 word into sign form. Yes, okay. This is 2's complement. Sign bit are represented as this. Okay, right. So this should be 1 0 3 zeros and 3 1. So 1 3 0 and 3 1, right, correct. Okay, so we have the size of operator. The size of operator returns the size in bytes of an expression or a type name. The operator is right associative. The result of size of is a constant expression of type size t. Okay. The operator takes two forms. Oh, it can take two forms. Size of. Okay. The second form, size of, returns the size of the type returned by the given expression. The size of operator. The size of operator is unusual in that it does not evaluate its operand. Okay. Okay. So we have size required to hold an object sales data, size of the p, then size of type which points to p. Ah, okay. Size of type which points to p. Size of revenue member. Alternatively, way to get size of revenue. So we have the most interesting of these examples is size of p. First, because size of is right associative, it has the same precedence as this. Okay, this expression right associative. This expression groups right to left. That is equivalent to size of this. Okay. Then second, because size of does not evaluate its operands, it doesn't matter that p is an invalid uninitialized pointer. Okay. Dereferencing an invalid uh, pointer, the operand of size of is safe because the pointer is not actually used. Size of need doesn't need dereference the pointer to know what type it will return. Okay. Under the new standard, we can use the scope operator to ask for the size of a member of a class type. Ordinarily, we can only access the members of a class through an object of that type. Okay. We don't need to supply an object because size of does not need to fetch. Okay. We don't need to supply an object because size of does not need to fetch the member to know its size. Okay. So we have the result of applying size of depends in part on the type involved. Okay. Size of char or an expression of type char is guaranteed to be 1. The size of a reference type returns the size of an object of the reference type. The size of a pointer returns the size needed to hold a pointer. The size of a dereferenced pointer returns the size of an object of the type to which it points. The pointer need not be valid. Okay. The size of an array is the size of the entire array. It is equivalent to taking the size of the elements type times the number of elements in the array. Note that size of does not convert the array to a pointer. Okay. The size of a string or a vector returns only the size of the fixed part of these types. It does not return the size used by the object's elements. Okay. So, because size of returns the size of the entire array, we can determine the number of elements in the array by dividing the array size by the element size. Okay. Okay, right. This is an old trick we can use. Because size of returns a constant expression, we can use the result of a size of expression to specify the dimensions of an array. Okay. The comma operator. The comma operator takes two operands which it evaluates from left to right. Like the logical and logical or and the conditional operator, the comma operator guarantees that the order in which the operands guarantees the order in which the operands are evaluated. Okay, write a program to print the size of each of the built-in type. Okay. Predict. I'm not doing that. Predict the output of the following code and explain your reasoning. The output of the following code. Okay, so size of x divided by it will give 10. Then size of p, size of pointer, this will be 1. On a 32-bit machine it will be 1. Okay. For 32-bit machine 1. For 64-bit machine, 32-bit compiler you can say 2. We dereference the so it is effectively pointing to this. If we dereference so it will get the size of the thing it is pointing to. So it is pointing to an entire array. No. Yeah, this see, p is pointing to an array. Now dereference it, we will get the first size of int, right? Here results in an int, right? Size of dereferencing, it won't be 10. Also results in int because it is okay. Maybe I can check this 4.29, section 4.9. This is 4.29. Create int 10 and it just said equals x, right? So it points to the first element. Size of first element, right? Size of p, okay. One, it should be 10 and 1, right? That's correct. Okay. So using the table, parenthesize the following expression to match the default evaluation. Okay, so 166 page, here I come. Okay, so we have size of has higher precedence than binary, right? Size of. Okay, parenthesis, it is right associative, right? So it will associate this. Um, hmm, better. There we go. Then so it will associate the entire expression okay. Then right associative, and it has higher precedence than relational operators. Size of f, yeah. Okay, it is right associative, right? So this will associate with this, and it is higher precedence than binary, thus. Okay. Then you have the comma operator takes two operands. It evaluates from left to right, like the logical and logical or in the conditional operator. The comma guarantees the order in which its operands are evaluated. The left-hand expression is evaluated and its result is discarded. The result of a comma's expression is the value of its. The result of a comma expression is the value of its right-hand expression. The result is an L value if the right-hand. Okay. One common use for comma operator is in for loop. Right. This. The loop increments ix and decrements cnt in the expression as in for header. Both ix and cnt are changed in each step. As long as the test ix succeeds, we reset the current element to the current value of cnt. Okay. So the program in this section used the prefix increment and decrement operator. Explain why we used prefix, not postfix. What changes would have to be made? Okay, what changes would have to be made to use a postfix version? Rewrite the program using postfix operator. What changes? Well, right. Okay, so we have to always action. Use prefix to avoid copying, to avoid storing the old value of the L value after it has been incremented. So changes is we will put a less than here, and then simply we'll go about with the same process. Okay, so rewrite the program. Okay, I'll do that. Okay, explain the following loop. we are iterating through an array of size 5. We have a pointer to an array. We are iterating through an array of size 5. Okay. We are iterating through an array of size 5. We have a pointer to an array. Pointing at the first element. And in the loop we make sure that loop we make sure that if pointer points, okay, in the loop we have a condition. We have a condition that order of evaluation we're iterating through an array. We're iterating through an array of size 5. We have a pointer to an array pointing at the first element. In the loop we have a condition. In the loop we have a condition that if the pointer points, the size is 5. Acha, we're incrementing plus, right. So this is 1. Okay, pointer points to 1 of the end address, and the size is equal to we have a condition that if the pointer points to one of the end address, points to one of the end address, and that ix is equal to that ix and that ix is equal to size of ix is equal to size of we stop. Okay, so I can rewrite this loop here. Success 4.10 section 4.10 sub this 4.31. Move from size to 1. Okay. Ah, oh, okay. So we have this, right? Okay. Hmm. So I would have to include vector and using studio vector. Oh no. I can use the out and print out. Okay. So we create a vector of int called ivac, and I want to put values, let's say 5 4 3 2 1. Okay. So assign value from size to 1 of the element in ivac. Okay. Yeah. So if you want to make it work with postfix operators, I would have to do negative negative ix. This should be ix is less than, yeah, x is less than size. Hmm. Okay, Vera. Dude, did nobody assign? Okay, they are not same type. And count. What is this? Count was not declared in the scope. Are you sure, my man? It is right there. Are you sure? Even this guy can see it. Zero of int size type. Okay. Alright, my bad. Yeah, 5 4 3 2 1. Okay, works great. Right. They have type conversions. Okay, the type conversion in C++. Some types are related to each other. When two types are related, we can use. Okay, I think I should. Okay, in C++, some types are related to each other. When two types are related, we can use an object or value of one type where one operand of the related type is expected. Two types are related if there is a conversion between them. As an example, consider the following expression which initializes ival to 6. Okay. About loss of precision. Okay. The operands of the addition, the operands I should be ready with mathematics. This is mathematics. Yes, Alex. Which I have to go with. Alright. The operands of the addition are values of two different types. Step double and 3 is in it. Rather than attempt to add values of the two different types, C++ defines a set of conversions to transform the operands to a common type. Okay. These conversions are carried out automatically without programmer intervention and sometimes without programmer's knowledge. For that reason, they are referred to as implicit conversions. Okay. The implicit conversions among the arithmetic types are defined to preserve precision if possible. Most often, if an expression has both integral and floating point operand, the integer is converted to floating point. In this case, 3 is converted to double. Floating point addition is done and the result is double. Okay. Right, the initialization happens next. And in initialization, the type of the object we are initializing dominates. Okay. The initializer is converted to the object's type. In this case, the double result of the addition is converted to int and is used to initialize ival. Converting a double to an int truncates the double's value, discarding the decimal portion. Right. Okay. So we can continue this next time around.